So although this chapter is called rotational dynamics, but it is not just dynamics. It is a lot more than dynamics. So I can say this chapter as a rigid body mechanics. So it will have variety of categories. So we'll start with something called statics, and this branch of mechanics deals with the bodies at rest. So it is also called equilibrium of bodies. The main name to this. And when we say body is at rest or at equilibrium, then we refer to two separate things. So one is called translational equilibrium, which simply refers to the fact that center mass is not moving, which means but the second thing is also called rotational equilibrium, which means something like alpha is zero. So this is the first part of the mechanics of rigid body. So
So,
that yeah,
so equilibrium of bodies that are divided into these two A and B.
yeah. If we say equilibrium, then we have to refer to both translation and rotation. Then we can say it is equilibrium. So, for example, if you talk about the ceiling fan at your home, so definitely the center mass of the ceiling fan is not moving, correct? So the first condition is met, but the blades are in rotation, correct? So when you switch on your table fan, then the blades will have alpha actually. So the entire body will have alpha, and therefore it is not in the rotational equilibrium. So we cannot say it as at equilibrium. So when we talk about the bodies and when we talk about the equilibrium, then we must make sure that it is at rest or it is not exerting either in terms of translation or in terms of rotation. So in both cases, we have to satisfy. So that's why it's difficult than the normal case. In case of particles, we only talk about the this scenario. So if you have studied the laws of motion, then we have already done this part. The A part is done. B part is something new to you, but not very difficult. So the idea is simple. The translational only deals with one particular point called center mass, but the rotational talks about the body as a whole. So we will learn about this, how to deal with. The second part of discussion will be dynamics. Now dynamics means the body will be in motion. It will have ACM. It will have. It may or may not have ACM. It may or may not have alpha, but both cannot be zero. So dynamics means at least one of the things are non-zero. So if ACM is zero, so you can say there are many conditions. So if ACM is zero, then alpha cannot be zero. If both are zero, then it is statics. If ACM is non-zero, then alpha may be zero. Or the best case is when both are non-zero. So when it is turning, sorry. So when it is rotating as well as translating, and both things are happening, so we call dynamics. So in dynamics, we study laws of motion, kind of thing like you write F net equals to mass into acceleration. but acceleration turns out to be ACM only, not the A. And apart from this, you get one more equation which is not commonly seen so far. It's called tau equals to I alpha. So now these two equations will govern the entire thing. So you need not to worry much. Just you need to add this extra equation, and we are done. Now, what is I will talk about later on. The third part of this discussion, this chapter will have is called rotational kinematics. So now this is the most challenging part for everyone. Like everyone feel difficulty here only. Okay, rotational kinematics, in which we talk about mostly constraint relation. Or interdependence of motion of particles of a body. So this is not the end. Now the fourth will be something called angular momentum, which is a analogous to the linear momentum, which we have learned in for particles. And the last discussion will be on the energy part. So it's like energy analysis, we can just say. So you can see that in total we have 5 departments in this topic chapter itself. And you may be thinking this is one chapter, but let me tell you, this is a complete one semester course of BTech first year. So this chapter itself is BTech first semester course in any engineering college across India. And probably by learning this chapter here, you will be completing your BTech first semester. And hopefully this will be more than what you will learn in BTech. Okay. So this is the entire discussion of rigid body mechanics. These are the departments you can say. And the way we start will be quite different. So we are going to learn this later on, the dynamics and statics. So how we'll start is the something here. Look at this. So this is the starting point for me. So this is a very silent feature which is just embedded in this equation. It is the base of all discussion. So once we understand this part, then we are kind of through with the half of the syllabus. Because once you know how to write ICM, then all other questions are pretty easy to apply. So our journey will be quite different. So now the kinematics part, this part I will take this later on. The reason is I have told Ramesh to inform you all that you must go through the circular motion chapter for the first at least 2-3 lectures, and then probably I'll start the kinematics. And meanwhile, you're revising that circular motion. I'll start the. I mean, I'll finish the moment of inertia. Okay. So the moment of inertia is something really big deal. Okay, so let me give you some motivation why we studied this chapter. So a body is nothing but a collection of particles. So when I say body, so now you are entering into the real world, correct? So because particle was just a concept, so nothing really like a particle exists in nature. So even the invisible object like atoms are having some dimensions. So they are not particles. They are of course having some dimension. They are like rigid spheres, and they have radius, mass, and moment of inertia and everything else. So now the question is why we are learning this chapter. So what I said is a body is a collection of particles. So now what is the big deal about this collection and the collection that we studied in the previous chapter called center of mass. So in center mass, if you remember that essentially we were learning about the discrete particles. So we have 10 particles and everyone will have their own position vector. And what we are trying to find is find the center of mass. So now this concept of system of particles is not only true for the particles which are discrete, or you can say isolated from each other. Rather, it is also for those particles which are somewhere connected. So let's say if I draw some particles in space and they are connected by some invisible transparent glass. So let's say they are connected by some glass, which you don't see. So now this glass frame is holding all these five particles. Let's say glass frame is massless object. So it is made of something really light, maybe carbon fiber. So now these particles which you look at right now, they are rigidly fixed now with respect to each other. And I have taken just few bunch of particles to demonstrate this fact. So now, if I turn one particle, let's say if I rotate about this line, so what do you think? Other points will be affected or remain same?
Affected.
So the motion of each particle is dependent on the motion of first particle or independent,
Dependent.
and that is the basis of entire subject. So the dependency, the moment we create a rigid body, the motion of every particle becomes dependent on each other. That's a simple idea. So now if you understand that if you have a rigid body, then if you turn one point, the obviously other point cannot remain stationary. They have to move with respect to each other. Therefore the motion becomes relative. Now what is the big thing about this, big deal about this is, once you know the motion of one particle, and once you know the rotational parameter like angular velocity or alpha, every other point in the body will have well defined velocity and acceleration. So what matter is, like, what we need to know as a you can say a variable or parameter or some, I mean you can say uh, constraint, that if you give me few number from a body, like body is a collection of infinite particles, you just give me some parameter, you give me some values. Okay, so let's say you give me velocity of center mass and you give me omega. The moment you give me these two values, I can tell you the value of every other point in the body. So no matter which point you choose, I can tell you the answer. Now the 2 points need not to be center mass and omega. So you just give me any value. Just see, no matter if I say that instead of this line, if I turn about this again, you can see all will move. Correct. Instead of this point, if I choose this point, then again the same thing will happen. So all will move. If I move like this, all will move. If I move like this, all will move. So the idea is you pick any random point, you give me its velocity, and you give me omega of the body as a whole. I will tell you the velocity of every other point. Now, if we talk about the which point is most convenient to find the velocity, in general it turns out to be center mass. I'm not saying it is always the case, but in general it turns out to be center mass, and that is the basic idea that center mass is a convenient choice. It is not the only choice. Now that is something which you need to take care of. So center mass is the convenient choice, not the only choice which can represent the motion of a body as a whole. So bodies are like collection of interdependent particles. And now the word rigid is something very beneficial. So the moment you say something is rigid, you make sure that the separation between the 2 points, let's say 1 and 2, this is going to be fixed. You cannot change that. So rigid only gives you this constraint. So the rigid will make us okay, take this criteria that the 2 points are at a fixed relative distance. Okay. So their separation cannot change. That's the basic of a rigid body. And from there we derive other formula. So this rigid body itself is a constant relation. So when I say a body is rigid, I give you one constraint. And what is that constraint? That choose any two arbitrary point in a body, and the separation will be fixed. Now tell me one interesting thing, that if two points are at fixed separation and they are in motion, so what kind of motion will it be? So if I choose one as the observer and two as the object, then which kind of motion you expect?
Circular.
Exactly, that's the only choice you have. Now this is something you have to realize, that a fixed point, if we have a 2 point which are at fixed separation, and if it is in motion, the only motion which is feasible in their frame of reference, like their way of observing, if one will look at two or if will look at one, the only way the two can move is at right angle to the line. Why? Because this is the only motion in which the separation will remain constant. And because the separation will remain always constant, so it turned out to be a circle. So now this is the second big revelation in this chapter called rigid body, that in rigid body, every point in a body with respect to any other point in the same body will only perform circular motion. Now that is the crux. If you know this fact, then you're done with this chapter. In fact, this is the most challenging part, which we all realize. So in case of rigid body, if I tell you the velocity of one particle, the other particle velocity with respect to the first particle is bound to be circular motion. And therefore, if I define the omega, then we can always write that v21 equals to omega, because it's a circular motion. This is always true, no matter what. So omega is a unique characteristic, right? Because if you have a body, let's say if you have a fan, or if you take any rigid body, the rigid body cannot have distinct omega, so it will have unique omega. So a body is well defined by its unique omega, its unique angular velocity. So body's angular velocity is unique quantity, and therefore no matter which two particles you choose, the omega between these two particles, or if you choose these two, the omega for these two as a relative, or you can choose something like this. So what do you think? The omega will be same for all, or will it be different? So if one will look at two, if two will look at three, I mean, so three will look at four, and four will, sorry, five will look at six. Will they see different omega or same omega?
Different.
Okay. If the intuition says different, then I need to explain again. So anybody else who think that it is going to be same? Anybody else? No.
So if
Char
one
is
is looking
changing
at
now.
two and two is looking at one, then it will be same, but not for others.
Okay. So now the fact is, if any particle will look at any other particle, all will be same, no matter which 2 point you choose, because it's a rigid body. Now what you need to realize, it's a body. So if it is a body, what does it mean? Okay, so this is something intuition we need to develop as a beginner. It's the challenging part. Okay. So imagine I draw two random lines, just one line and another line. And imagine it's like some plane surface. Okay, these are two lines which I've just drawn randomly on this surface, and it's a some sort of sheet, a rigid sheet. If I throw in the sky, I mean just anywhere, what do you think that the separation between them? Let me extend this line. Why don't we extend this line? So I can do something like this. This is the angle between them, right? What do you think? The angle between them will change or remain same?
Same.
Because both the lines are on the rigid body, so the angle will be same. So now let's say if it is 1 2, this is 3 4. If 1 2 will turn like this, the 3 4 has to turn in a way to keep the angle same or different.
Same.
Now that is only possible when both will turn by same value. So if it means if 2 comes to 2 dash, then 4 must come to 4 dash in such a way this angle is still the same as the angle before. It means both will turn by same value. If it is not the case, then this will not be true. So what you need to realize that the rotational angle between any two points must be same, which makes sure that omega is a unique property of a body. So omega is a unique property of body. Can we say velocity is a unique property? Tell me, guys. Can we say velocity is the unique thing?
No, sir.
Correct. So velocity of every particle depends on who is watching it, who is observing it. So now we know V equals to omega R. So because omega is a uniquely defined thing, so V will depend on, so you can say V is, now here V means V relative, because I'm talking about the 2 points in the body. So omega is a unique property of a body because it signifies that how much body has turned over a given time. And if we draw to any number of imaginary line on the body, every line will turn exactly the same. So no matter how many line you draw, every line will turn by the same value, and that is what we understand that omega is a unique quantity and velocity is a distance dependent quantity. So if you look at the fan again, I will take the same example, fan, ceiling fan. Which point of the ceiling fan is moving fastest?
Sir, the
So
end
the
point.
end, yes.
Correct. So end velocity is very high compared to the velocity at the center. Center is 0, correct?
Yes.
So you can see that one body with infinite velocity. But what is same for them? Omega. And although all particles, I mean, all particles are moving on a different track with different velocity, they end up maintaining the body shape because the body shape is determined by the relative movement, not the absolute movement. So you can see that to keep the blade as one entity, the particles of the blade has to move with different velocity to maintain the alignment. So one on the perimeter will travel more and one close to the center will travel less. You can see this is the travel. And one closer will travel lesser, least, and this is will turn nothing. So a rigid body makes sure that the entire particle turn by equal angle. So angle is a quantity which defines that the rotation. And having same angle does not guarantee the same displacement. So this is R1, this is R2, something more, something like R2, R3, and so on. Or S will be the distance we are. So what you can realize that for a rigid body to act as a rigid body, the omega need to be unique. So I hope you have realized this. The omega must be unique. Omega is unique will not guarantee the velocity is unique. And now why the omega should be unique is obvious. It comes from the definition of a rigid body. So when you say something is a rigid body, that is a natural choice. I mean, omega need to be unique thing. So that's why in a body, our larger emphasis will be to understand the omega definition in detail. And from there we'll define the motion, and from motion we'll define the other things. So now this kinematic, this rotational kinematics, why I'm saying this is challenging, because here you have to understand the entire property of a rigid body in terms of how they behave, how they move, how one moves with respect to the other, and why the circular motion chapter is so important. Now that you will realize. Okay. So if you look at the tip of the blade of your fan, which is in motion, and if you take the tip, just mark this blade by some circle using sketch pen, and you can think that as a particle. And if you look at that particle, you know it is moving in a circular path. So who must be providing the centripetal force to that particle? And answer is simple. It is the remaining part of the blade which pushes that part of the. Okay, I mean I need to do something. I mean, you guys are getting confused. So if this is the blade, just to understand, this is blade, and let me draw a small particle at the end, and the blade is definitely in rotation like this. So now this blade, sorry, this particle, let's call it m mass. So what you don't realize that even this is moving in a circle, right? This is the circular motion, correct?
Yes.
So this requires centripetal force. I mean, this is what you need to realize, that this particle will follow a circle if it is having some centripetal force. And therefore, this force, if I ask you the question that who is providing this force to this elementary particle dm, the answer is the remaining part of the blade, this part of the blade, except this part, all remaining part. So a rigid body develops this centripetal force which pulls or push the one part to the other part. So imagine if I give you something like a simple rod. So imagine if I give you a rod and you throw the rod, you throw something like this, it turns, it turns, it turns, it turns. So it is turning like this. So I have taken the photograph at different instant. And not only just turning, you can see that center mass of the body is also going forward, right? And you will realize later on that the center mass follows exactly the parabola, like what we studied in the
Parabola.
chapter of projectile motion. So no matter what is the shape of the body, the center mass will act as a particle, and the particle will perform the parabolic path. So you can also understand that omega, the rotatory property, it never affects the motion of center mass. So omega is a unique quantity. It never affects the center mass motion. So if center mass is a particle, and if you imagine that what would have happened if you have thrown a particle from the some place here, so we know in advance that this will make a parabolic path, just like a regular projectile motion. So the center mass path is well defined always, no matter what is the shape of the body. So if I give you a shape which is, let's say, like a rod, or even if I give you a random shape of object, and if I throw it, the center mass, if I define, it is bound to follow parabola. Now body can have any position, but the center mass cannot change the position. It is going to be same. So the first thing which you need to realize that The rotational effect of a body never affects the translational effect of center of mass of body. The other points gets affected. Yeah, that is true. So if I talk about this point will move in a very complex path, because you can see this point is turning in a very, like, I cannot define the path. So the idea is, in a body, the center mass again is a unique point which follows the pure translatory motion properties. It means everything you studied in the laws of motion chapter, you can exactly apply here, but for center mass. You cannot apply for the other point. You cannot apply for here, for this point, for this point. No, you cannot apply. So center mass is a point which follows the properties of translatory motion, and therefore you can just deal with the laws of motion and take the center mass as your particle and discuss the motion. Don't worry about the rotation part. So rotation is like something like superposition. Okay, it is like something like superposition. So you superimpose this motion over and above the, you can say, translation. So for example, you can imagine this way. So how to understand this motion? So take a wheel, you just take a wheel. So imagine you have taken a wheel. Uh, let's make a hub. So now let's say wheel will have some axle attached here. So I'm not showing that axle. And you give a big omega. So you spin this wheel. So now this is now moving. So I'm trying to animate this motion. Now, once you set this into motion, you can realize something. You can realize that this every particle is moving in a circle, correct? Can you see that?
Yes.
And you're holding here, you're holding the Excel. So Excel, it's just like a, that Vigat spinner if you have used somewhere. The figure, what is it? Figure spinner, yeah. So then the center you hold, right? This is center you're holding. Now wheel is moving. Now imagine that a person holding this Excel. I mean, this. So holding this Excel, and then you hold this in your hand and you start running. So you're not letting it move on a road, but you're holding this hand and you start running here. So if you run, then omega will get affected, yes or no?
No.
Definitely. So now imagine the bicycle. Okay, so bicycle, the wheel will have omega because it's turning, but center mass of the wheel, which is the axle, will also moving forward. And the ground is acting as a constant. It is saying that, see, I am not allowing this point to move. So that I will discuss later on. So when a wheel is moving on a, on a surface without slipping, then the V and omega gets connected by some relation. So we'll learn about this constant relation, which is V equals to omega R. We'll learn about this later on. But in this particular case, when you're running, then it is not necessary that this V with which you are running, holding the axle, and the omega will have any relation. So you can run slow, you can run fast, but the omega will be same. So omega and V can be dependent as in this case, can be independent as in this case. So dependency depends on some extra constraint we put. So let's say we put a surface beneath the wheel and we make sure that it is not slipping. So when you say not slipping, indirectly you put a constraint. So this is like a constraint. We are putting extra constraint. And the moment you put the extra constraint, then V and omega start binding with each other in a formula. So that is something which we'll discuss later on. So this is just a motivation to understand that the motion of a rigid body is basically superposition of two motion. One is the center mass motion, and the motion of the remaining part in the center mass frame, or you can say omega. So omega and V, if you superimpose these two, then you get a third variety of motion, which we call combined motion. So we have a separate chapter called combined motion. Now, this is all a part of this part, kinematics. So rotational kinematics is one hell lot of a thing we need to learn and master, and that is the most challenging part of this chapter. The rest 1 and 2 and 4, I mean 5, 1, 2 and 5 are very pretty easy, just like what you have learned so far before in your laws of motion chapter or circular motion chapter. Nothing more about that. Okay, it's pretty simple. So you can see there's only small changes. ACM has come into picture instead of A. So let me give you some simple example before we go to the actual topic. So imagine if I give you a rod. See how easy is the physics. So even without teaching this, I can tell you how to apply this concept. And if the rod is fixed about this end, so this is moving about this end and it's turning with omega or maybe alpha, I can say. Yeah, let's say omega, as of now. Omega. The length is L. Now you all know where the center mass, correct?
L02.
Correct. Now, if I want to write the force, because this is a hinge, this is called hinge, some sort of you make a hole and put a nail inside so that you can turn around this. So this is called hinge in physics language. So now to write the circular motion, we need to think of center mass, not the body as a whole. So just we need to forget about body. Think of center mass. That's it. And now you can see center mass is moving in a pretty simple circle of radius L/2. So the question is how much force is applied by the hinge. So I know that the centripetal force must be provided by some external agent. So for this rod, the extra force will come from the hinge itself. So there is no other thing which can provide the force. So I can say the hinge reaction R, which is like a centripetal force, equals to mass of the object into AC. That's it. And now
So what is R?
R is the hinge reaction force. It's a force only. The force applied by the hinge on the rod to pull it towards the center, correct? So although the force will act at the hinge, but it is for the center mass. So center mass will experience that force. This is how we think. Okay. So what do you write net force equals to? Mass into acceleration. And what is the acceleration? Omega square R. And what is
V
R?
square by R.
L/2. So V square by R or omega square, you can choose whatever. And now you got the laws of motion equations. Of course, we'll learn in detail, but what I'm trying to demonstrate here is simple idea that the chapter is not difficult because you just replace the body by center mass and deal with as you have done before in the laws of motion chapter. What is difficulty is this part, the kinematics. So we have to spend a lot of time in kinematics. But I do not want to start kinematics right away because the reason is I want to finish the derivation part of some mathematical integration part, which is calculation of this IC. Because I don't want to bring the integration in between the discussion of physics. So physics should be separate and math should be separate. So we will do the mathematical stuff right now and we'll complete for once and ever. And then we start the physics part. which just required concept. No need to worry about the derivation. Now derivation is for, of course, if you are thinking of a J advanced, then derivation is a must. For rest, those who are not preparing for J advanced or like medical guys, I mean, for you the formula is must. And apart from the formula, there are two famous theorem in this particular chapter, which we learned as parallel axis theorem and perpendicular axis theorem, which is kind of a shortcut tool to avoid the derivation and get the answer direct. So we'll see the this concept first, and then we'll come back to the physics of dynamics. So I'm not going to physics right now. I'm going to mathematics.
So can you show the hinge page?
Okay, you want to know? Yeah, this one.
Yes. Run.
Okay. So now what we're going to start today is called moment of inertia. This is very important chapter, a topic in fact in this chapter. So I think you are aware of the word inertia, right? This is something known to you. So what is inertia? What is inertia? Come on.
A tendency of an object to be in the state which it is.
Yeah, so the state of rest or motion, whatever they want to maintain it. So inertia has come from the word, okay, again I have given this, but inertia has come from the word inert, which is lifeless. So the idea is something lifeless cannot do anything, and cannot do anything itself is a property now. It means you have no idea what to do, so you just be what you are. That has come that is given the property inertia, which means if I keep the object on the ground, it will remain there forever because it is lifeless. It cannot start walking one fine day. Okay, I'm getting bored here, let me go to some other place, find some best beaches in the world and go there. No, they will be there forever. So now because they cannot do anything, that is called inertia. That's it. So similarly, if I throw some object with some velocity in a gravity free space, let's say there is no force at all acting, there is no gravitational force even acting, it's a gravity free space and vacuum, there is no air resistance and all. So once you throw, it will move forever because again the same, it cannot do anything. So if you throw, if you give some velocity, it will carry that velocity because it cannot do anything, it's inertia. So inertia we define in two ways: inertia of motion and inertia of rest. So inertia of rest, and we have inertia of motion. It's like a recap of previous chapter. So inertia of motion we represent quantitatively by the definition of momentum. So momentum is the quantity of motion. That's a basic definition, or mass times velocity. That is as what we have learned. So momentum is a mathematical measurement of inertia of motion, if you remember. So what was the measurement, or you can say quantitative measurement of inertia of rest? The answer was mass. Now to realize this, I mean, you need to take something really, a smooth surface, which is very difficult for you. But if you take a smooth surface and if you put a heavy object on the surface, let's take two iron cubes. Okay, that is readily available. You take two iron tube and put on a frictionless surface or a tiling surface with some lubricant on it, and then you push them by the same effort. You will see or you feel that it is difficult to push the heavier one. Or let's say if
So
you
can
at
you
home, if you take two heavy objects, two objects, one heavy, one lighter, and if you keep both of them on a frictionless surface, and if you try to push both of them by the same effort, you can feel that clearly the lighter one is setting into motion easily, but the heavier one is not setting into motion easily. It means you provide lesser acceleration to heavier object and more to the lighter. That's obvious, correct?
yes.
To feel this gravitational, I mean, if you see normally in our day-to-day life, we are surrounded by a variety of force which we don't realize. So you can do one experiment at your own risk if you can do, because I have performed this in class. So you find some of your siblings A and B. There's a sibling one, okay, sibling two, okay, and then this is the experiment you can perform at home under the supervision. So now a person will be acting, sitting here, I mean, standing here to safeguard the fall. I mean, you should not fall backward, else you will injure yourself. Or you can wear helmet. And this is really fun. I mean, you can feel the physics at work. I mean, this is quite thrilling, more than any joyride in your life. So now you hold the palm of each other, stand close by, nearby, like you stand and you just hold the palm like this. And one should be heavy, one should be lighter. So this is lighter. Maybe one is 80 kg, another is 60 kg. Now to feel the physics, you jump at the same time. So both jump. In the process of jumping, just push each other. You have to push both of them each other as hard as possible. And then you will realize that you will actually fly off. So now the 60 will go very far and you will go less direction. You can feel that. And then you will land back on the earth, ground, you will not fly very high. So heavier object will have more difficulty to set into motion. So the inertia of rest is the measurement of this difficulty. So mass is the a quantitative measurement that how difficult is to set something into motion. So it is the measurement of difficulty. Okay. I hope the mass concept is clear to all of you. Okay.
Yes.
So when we study mass in this particular context, this mass is called inertial mass. Okay. So there are a variety of name for the mass. So you know one mass, but there are many mass. So we have inertial mass. We have gravitational mass. We have a relativistic mass. We have Bose-Einstein condensate. So there are a variety of mass. These all are masses. But Einstein proved that the gravitational mass and the real inertial mass are same. So no need to worry. I mean, now for you the mass is only mass. So you really need not to distinct the mass in variety of ways. It's a pure concept. It's a very infinite concept, deeper into nature. Anyway, so the idea is simple. The role of mass is very much clear. Like if you know physics, you should know that mass is only a mathematical concept. Like it is a property of a body which you don't see at all, but it is the property which gives rise to the other property, other phenomena, you can say. And to quantify this property, we just defined mass. Okay, so now in physics, the mass is actually it is a concept, but we also have some measurement, criteria which we have designed. So you know that 1 kg is a platinum cylinder, platinum iridium cylinder kept in the France, right? In the Sevres, say that the IUPAC definition.
Yes.
So there is nothing real, You see, some random guy chose some random size object and called 1 kg. That's funny thing happening in the world. But of course, these kind of measurements are it was necessary to actually facilitate the commerce and trade between the countries. That is the basic idea behind the units and measurement chapter. So if you study the units and measurement chapter, the whole purpose is to facilitate the exchange of goods or exchange of goods with currency and so on. So we need to set some metric. We need to set some standardized system so that we can do the exchange on a rational level, not irrational. Okay. So anyway, if let's say one fine day people are very hungry and let's say you have only 1 kg of rice at your home, then you are the richest person in the world because that 1 kg rice is worth of billions of kg of gold. Because the gold cannot let you survive, but 1 kg rice can let you survive for some time. So that you are the richest person. So in terms of commodity exchange, we need to set some standard, some metrics so that we can do the exchange. That is the whole purpose of unit and unit chapter. Like, why we create units and so and so. So mass is a quantitative measurement. Okay, so it is some way to represent the difficulty of setting something into motion. And when we study mass in this particular context, we call it inertial mass. Okay, so the second thing is the difficulty is not only in moving the mass, the difficulty was also in rotating the mass. And then the obvious question is how to set this metric into place. Like I know that to move a heavy mass is more difficult. Fine, well and good, not an issue. But if I want to set something into rotation, that is also difficult. So now my question was like how we can set this difficulty into some mathematical format so that we can compare the two difficulties. Like if you say that my difficulty is bigger than your difficulty, there should be some method, some metric, some measurement which we can employ. And you want this, and can I remove this? Not equal. No? Yes, I remove this part.
So,
So yes.
so inertia is moment of mass moment. No?
Hmm. Inertia is the difficult moment of inertia. You are talking about moment of inertia, correct?
Ah, yes.
Yeah. So moment of inertia is the difficulty of rotation. Like how something is difficult or easier relative to each other. Like that is the idea of moment of inertia. And it's very intuitive. It's not difficult to understand. Let's say if I give you a mass, so I give you one simple object. So let's say I give you a small object like some spherical rigid body, maybe a pendulum. That's a nice one. And you attach with a thread. And taking this object and this thread of length r of mass, this is a really small object, so don't consider its size. It's negligible. Let's call it particle. And you set this into rotation. So you put this on a floor, maybe something like this. Maybe. So you set this into floor, moving. So the idea is simple. If you set this into floor, then you need some. You will. It will take some effort to set it into motion. Right? You take the thread and you move your hand, and then you make sure that it turns. So it's not so easy. So generally, if you want to set something into, I mean, something which you don't realize, something not challenging. So you want to set this into motion in some circle, then your hand will also move in a circle. You realize this? You move something, then your hand also turns. You just take a small object and take a small thread, and try to build it. You will feel
Yes,
that
sir.
hand, your hand holding the rope is turning in a circle, not it is not a stationary. Now that is something interesting. You don't realize, you know, it realize that to move something in a circle, you also move your hand on a circle because that is how you pull it actually. Anyway, now, what is the idea?
So,
The
so
idea
that
is,
creates the centripetal force.
yeah, because this will have the tension. No? So if you actually pull tangential, then how it will turn? Common sense, isn't it?
Yes.
So actually, you pull in a way which creates a centripetal force which let it turn. Actually, so that is what we need to do actually to set into something rotation. Now, the difficulty is if I increase this length, if you go really far, then you can understand that if it is really far, then this angle will become very close to 90, right? Close to 90.
Yeah.
And therefore, providing the centripetal force is more difficult now, isn't it?
Sir, what?
Then this tension will not provide the sufficient centripetal force, isn't it?
Ah,
Now, this
yes.
gas, the component will be very small, no? Toward the center.
Yes.
Yes, sir.
Cos 90 is zero, no? If you know. So if you it is really far, then it is very difficult actually. I mean, this is something which you don't realize on our day-to-day life. What I'm trying to say that you need to make a circle bigger. So now what will do? You will make a your bigger circle of your hand. Now that is your hand having limited radius. You can't move your hand beyond certain length, isn't it? So after a while, then with your hand you can move. You must have realized that if I make the thread really large, it cannot set into rotation. I hope you can imagine this phenomenon. You cannot do that.
Yes.
So the idea is simple that you cannot rotate everything with your hand. So then what you do next? Then you take the object and then you start running on a big circle. So you run as a person. So you create a big circle than your hand by running, holding the end and running and then trying to set into rotation. Now this whole idea we can combine into one small concept. So what I'm trying to do is that although the mass is the same object, mass is not changing. But if I increase the R, what do you think? The difficulty will increase or remain same. So will it be more challenging to set into rotation if I increase the R?
Yes.
So as R will grow, the difficulty will grow in measurement or will decrease. What do you think?
So grow.
Correct.
Yes, sir, it will grow.
So now what you need to realize that the moment of inertia, which is a difficulty measurement, in simple terms, I say this is the difficulty. It will grow with R, but I don't know exactly what is the relation. What power of R will let it grow? So it will grow with R with some power A, and definitely even if you keep the R constant and if you if you change the mass, it is also going to proportional. So more the mass, more the difficulty. That is obvious. I think with mass, the difficulty will be proportional. That's obvious, and it will have some power. So definitely, it is bound to be some power of MBRA, something like this. So moment of the difficulty of setting a mass into rotation is not only about you know mass. It is also about the how far is from the no. There is something interesting. Axis of rotation. So how we define the R? How far we have put this object from this axis of rotation. So the axis of rotation is something very interesting. That this defines that if you want to define the motion about this line, then what is the difficulty? And definitely, if I change the line here, I can say difficulty will decrease. And if I bring the line here, difficulty will be least. And if I bring the line here, it is again more. So axis of rotation is the interesting concept. We need to understand that the axis of rotation will tell you the R value. Unless you will not define this axis, R cannot be defined. R is not something absolute. It is something relative to the axis of rotation. I hope this is intuitive. I mean, not very confusing.
Yes. So just one question. So what did you prove the definition of I? Difficulty of setting mass to rotation.
Yeah, it is like the relative difficulty or easiness to set something into rotation. It's a relative. Compared to what? Let's say if I say my difficulty is 100 and if your difficulty is 200, so your mass or your object is twice as difficult to set into rotation as my object. That's the idea.
Yes.
And if someone's difficulty is 10, then it is 10 times easier than my case. Okay, so if I have to turn something, like I have some object to turn and you have some object to turn, your object is only 10 times easier than what I'm doing. That's it. So once you have this measurement, then you can actually compare two rotation, right? That is the whole idea. So to compare the difficulty of rotation of two mass distribution. Okay. Now this is something simple. So this was derived very easily using the energy part actually. So if I talk about how it is derived, so it is it is very easy to derive. I will tell you. So I will not take much. Uh, so imagine if I just take one part, like if I really want to know what is the derivation, it's very easy. And let's take a particle. I mean, I don't want to make it a body. We'll take a particle. And if the particle is rotating about this axis of rotation, the distance is r mass m. So what is the kinetic energy of this particle? It is simple half m v square, right? That's simple. But because of circular motion, v equals to omega.
Omega.
So now the kinetic energy you can rewrite as half m omega square r square. So now, as I said, the omega is a unique property of a rigid body. So if I remove the omega square separately, then you come across something new here. You can see something else. And therefore, I wanted to, or in fact, you can say we wanted to convert this into some sort of a rotational property. So we define this as I and we wrote as. And from here, we derive the formula that I is equals to m. So now you know what is A, what is B. You know, so A is 2 and B is 1. Right? This is what I said here. So M is 1, B is 1, right? And R is A is. Do you realize this?
Yes.
So the moment we want to express something in the rotational form instead of translational form, I mean, instead of a particle, if I imagine a thin, invisible glass rod attached between the mass and the axis, then this will be like a rigid body. And the kinetic energy of this rigid body as a virtue of rotation, is this much, and then I is this value. So now you know the formula of moment of inertia. It's pretty simple. It is m into r square, and that is also a common experience that as r will grow, the difficulty will rise. That is what you can realize, right? So
Yes.
now the simple question is, what exactly is moment of inertia? What it signifies, visually, what we can realize. So it
So
talks
can you
about
explain that diagram? That
which one?
pendulum diagram.
Which this one?
Yes.
So this is the mass. This is the experiment I'm saying. This is the experiment, and this mass is located
So not that
at
right, sir.
the
The right one.
this one.
Yes.
Okay, this is what I said that to set this body into rotation, we need to move our hand into circle also. This is the thread which is attached to the object. So you pull this thread, no? You pull this thread, and then you move your hand like this. And the tension developed in the thread will create a centripetal force, which will set this into circular motion. If you are doing with your hand, okay. So we need some force, something like this. If you actually apply the force tangential only, then you cannot turn, isn't it? So you can do this experiment at home. Like just take something thread or attach any object, a toy or something, and then try to move, and you will realize that it's common sense. Okay, so what I'm trying to say that when you turn something with your hand, you need to move your hand in a circle. And if you want to move something in a big circle, then you also need to create a bigger circle of your hand. And therefore, if something is really big, if the thread is really large, then it is impossible to move something by your hand. In that case, what you do is you start running on a track and you make sure that you provide that.
Yes, understood.
So, so we got some intuition about the moment of inertia. Intuition we got for a particle. So for a particle, the moment of inertia is mr square, but r is the distance of a particle from the axis of rotation. That is the important concept. The distance is a perpendicular distance or the minimum separation concept. So there are a variety of ways in which you can define moment of inertia. This is the mathematical definition. So let's go to the non-mathematical definition, the definition which we need to internalize in our thinking process, and that is the difficult.
Sir,
Say that someone said something. Yeah.
sir, how did we directly like equated I equals to mr square?
By comparing the the formula, like I have formula half mv square. So now the v is the characteristic of translation. Omega is the characteristic of rotation. And therefore, whatever remaining I have named as I. So if I remove omega square separately, what I'm left with?
Mr square.
So let's call it this as I. Now this is the
Yes, sir.
original way of writing in it. This is the translational way of writing. Okay? Not
Yes, sir.
so these are equivalents. See, as I said, every rotation you can either think as an infinite particles translation or think as one body rotation. It is up to you. And definitely, because we have discussed that omega is a unique property of a body as a whole. So instead of dealing with every particle, it is obvious that we will go with one unique variable. So instead of infinite variable, we want less variable, and omega offers you that opportunity. So of course, if you want to convert something into mathematical format, you want to reduce the number of variables, isn't it? That's how we solve mathematics. So the entire purpose of mathematics is to create as less equation as possible and as less variable as possible, so that it can be solved. Now, when you study the gaseous state of KTG, there how many particles we have? Infinite. It's Avogadro number of particles. And with those many particles which are not rigid, what happens? Now, gaseous particles are large in number, but not only large, they are also not connected.
Yes.
So they are independent particles. Like in rigid body, they are dependent particles. In gas, they are independent particles. So both are same situation. But see the problem. You cannot apply the laws of motion. I mean, you see, you cannot deal with the laws of motion and solve the question. The reason is infinite particles requires infinite equation, and we cannot solve the infinite equation. Correct? So
Yes.
because you cannot solve the infinite equation, then what you do? You bring a new theory called the statistical physics. And what it does, it describes the probability of motion instead of actual motion. So you start the guesswork because of large number. This is probable. This is unbiased motion. So the probability of hitting the wall on the X, wall on the Y, wall on the Z is equal. So the overall probability is 1/3. So the probability, we assume that the gas particle will hit this wall or that wall or that wall, is 1/3. So instead of dealing with laws of motion, we describe the motion of one particle, and then with the help of guesswork, or you can say the law of probability, which is quite true for the system of such a large number, we end up creating a model called statistical model. Okay. And with that model, we derive some formula called VRMS, V average, V most probable. And see, the name says most probable velocity. It's the velocity which is most probable in terms of numerical value.
Yes.
So these are models which we design to study such system. So in gaseous system, the model is statistical model. In rigid body, we are lucky because although it is again a collection of infinite particles, but we are lucky because they are dependent on each other and their motion is not independent, as we have discussed, which means knowing the motion of one particle will make sure that we can also explain the motion of other particles. Now that is the idea behind learning rotational. So now you can understand that the gaseous state and the rotational are two diametrically opposite systems, and their behavior or their motion is so unpredictable in one case and predictable in other case that we need to design a new model of learning, and which gives rise to the concept of statistical physics, which is nothing but a branch of physics in which we deal with the models of probability in describing the motion of particles. So that is true for any crowd, any chaos. Let's say you may behave differently, but when it comes to, let's say, if I'm the Amazon, which is the biggest e-platform seller of goods, so they use the statistical model to predict the consumer behavior because for them the consumer is really large in billions. So they use the statistical model using the machine learning and artificial intelligence because eventually this machine learning and artificial intelligence is nothing but a basic theory of probability, which you will learn if you study these chapters. So what they do is they use the same gaseous model. Okay. That if one consumer will go towards this brand or that brand. So here we have three walls, and there we have, let's say, 3,000 brands. Okay. So they create a 3,000 dimensional space. And every consumer will have the choice of going into any of the brand, and therefore the probability is 1/3,000, and from there they create a model. So statistically they determine the behavior of consumer across various brand domain, liking, disliking, and the same thing happens with the Spotify. The same thing is happening with the Netflix. The choice is modeled using statistical phenomena, and because the number is large, it is a big large scale platforms. So they have a large number of base of consumer which can actually set into the statistical behavior. So now you understand that how physics is so important if you want to learn any thing in future. You should know the physics, chemistry. I mean, this part of chemistry you can say gaseous state and the statistical modeling part, and a bit of quantum physics. If you go in BTech, you will learn about quantum physics. Then you can actually see the entirety of the world. Now, the entire medical science is going to be crushed into data. So now we know that a particular patient will have particular disease based on his history. Now I will put the history into a machine learning algorithm of billions of patients across the world, and it will predict the pattern in that. So now the various case will be easier to understand, okay, because of this particular absence of beta vitamin. This is most probable, this is less probable. So again, this is the theory of probability. So now that is not, I mean, our discussion right now. Our discussion is the a model called the rigid body, which is very nice model. So in a rigid body concept, what we do is we have infinite particles, but don't worry about it. So the infinite particles are interconnected. They are not like discrete in nature, they are connected, and therefore the entire behavior is a predictable behavior. So if I know the motion of one particle, I am almost very close to understanding the motion of any other particle, and that is what we are going to learn. Okay. And now this MR square is the consolidation of the difficulty into one single variable I. So again, what we're doing is we're trying to reduce the variable. So instead of writing MR square, we're just writing I. So if I give you a table of I for various kind of bodies of particular shape, which we often interact with, then you reduce the calculation. So now your effort is now reduced to one small number, and then you deal with the number. Okay, so every model, whether it's physics or it's computer science, they all are based on certain algorithm, and the algorithm is nothing but the basics of physics and mathematics. So nothing is more than that in the world. So whether you are the top-notch data scientist in the world, what you know is the basic of physics and maths. So you don't know something bigger. I mean, there is nothing more than class 12 physics and maths ever in the world. Okay, so to become a Nobel laureate, what you need to understand is the class 12 physics. That's more than sufficient. Now, after that, everything is cosmetic. Now, those who are not good with the basic of physics, they feel something new they're learning. Okay. So I feel that okay, even if I'm learning this, I'm learning machine learning and data science and all those things. I feel it's class 10 syllabus, class 12 syllabus, not more than that. It's very easy. But you need to have some deeper understanding of basic physics and maths. So I equals to mi square. Now this is like a model. You convert something into a number called I. And now it's easy to deal with I instead of dealing with mr. Correct? So what is the definition? The non-mathematical definition of moment information. So I gave you example with the help of one particle. Now what if we have many particle system with a large number of particles which are somewhere connected to make a rigid system? Uh, let's say the ball and stick model of organic chemistry. So you have stick, you have ball, you connect them to create a shape. Now that is also a rigid body structure, isn't it? So you can think that H2O molecule, maybe it's a H2O for you, but it is a three-dimensional pattern. So we have O atom, and then we have H atom. So I can think this is M, this is M, this is 16M. So now to set this into rotation, just need a number called I and omega. So I am not worried about each mass separately. So you just give me ICM, and if you set this into rotation, I'll come to know I omega square. So I know the energy of this molecule as a rotational unit. Okay. So you take any molecule and then it will have the rotational energy. It will have the translational energy, because this as a whole will also move in space. So when you move as a whole, we call translational energy half m VCM square. But if I am sitting at the center of mass, then if I look at your motion and I may see this is the rotational happen, then I define this energy. So now a body which is consisted of variety of particles can have two separate energy. One energy which is due to the motion of center of mass, which we call translational kinetic energy. Another which you set into rotation. So because see, setting into rotation is also difficult and it requires some sort of work, and therefore the energy possessed by body by virtue of rotation we call rotational kinetic. So kinetic energy is of two types. For particle, it is only one. So in for particle, you just at half mv square. Why? Because the particle cannot have omega. No? So if I have a point, then the omega is meaningless quantity for point. So now you know why we need to study this, because additional property will come into picture from the property which we have learned for the laws of motion chapter. So, so what exactly is moment of inertia? Definition simple. We say that it is the measurement of relative distribution of mass. It is the measurement of a relative distribution of mass around some axis of rotation. Okay. So the idea is simple. Closer the distribution, lesser the moment of inertia. Okay. So it is simply idea that if I give you one axis of rotation, which is called the axis, and if I have a connected mass, if I have a connected mass around that axis, which may be on the right or left or across, around, then the how closer you distribute. See, closer means the separation between the axis and the particle should be really small. So if I have a particle, one particle here, one other particle here, and if I attach them with some invisible rod, massless rod. Now this is the important. This is called axis of rotation. So again, to define the moment of inertia, the first thing we need to define the axis. Once you know the axis, everything is well defined. Now the distance means the perpendicular separation. Okay. So if I draw a line like this, and if I have a mass somewhere here, now the side doesn't matter. On which side it is, it really of no use. What matter is the separation. And the separation is the perpendicular separation, right? Okay. So moment of inertia will give you the idea that how close or how far the mass is distributed, and if you are getting a lesser value, which means the mass is really close to the axis, and a bigger value means it is really far from the axis. So now let's take simple one. So imagine a cone example that we have solved in the center mass. So it may be hollow, it may be solid cone, it doesn't matter. What matter is this. If I give you cone, and now But this is a cone, some random object. So cone is, you can imagine, as a mass. A mass is distributed. And now I draw some axis. I think common sense you can tell me. So tell me, if I choose some axis and let's say this is a solid cone. And as homework, if you remember, the center mass was how much?
H/4.
H/4.
Very good. So h/4 is the distance. Now I name the axis I1, I2, I can also now call it ICM, because if it is going through center mass, we call it ICM. The common sense, without learning anything about formula or anything about physics, you can tell me which one is going to be most difficult, I1, I2, I3. So arrange the order of I1, I2, I3 in terms of difficulty in increasing sense. So the least,
I1, I2, ICM,
so which one is the least
ICM,
and then next is bigger than
I2,
I2
I2,
and then
and then
I1.
see, of course, you do not need formula for this. You know that by definition, it is the mass distribution around the axis of rotation, and the closest distribution is by default the axis which passes through center mass. So if you are closest to the axis, if something is, if the center mass is on the axis, now that is the, for for sure, it's the least of all distribution. Okay, so the mass is actually closest to the center mass distributed, and this is going to offer you the least value of motion, no matter whether you know the formula or not. But quantitatively, you can say this without calculating anything, and we'll come to know that, of course. So if I give you a disk, let's say if I give you something like so if I give you a disk, okay, and if I just do the axis randomly, so which one is, of course, lesser? I see.
ICM.
This is more than this. Now, the real confusion comes because these two are parallel, and then now the third I am done, which is also passing through center mass. Now this is also IC. So the idea is, if you don't compare the axes which are not parallel to each other, so ICM dash and ICM both are passing center mass, then we need to again compare them separately. For parallel case, it's simple. If I draw multiple lines which are parallel, and if one of them passing through center mass, then definitely this will be the least value. But if we have a different plane, if they are not parallel, then we need to think separately. We cannot just guess from there. If I ask you what do you think, like by your inspection, what is the relationship between these two in terms of which one is bigger or lesser? Just imagine, like imagine the mass distribution, and I hope you can realize what I'm trying to say.
Sir,
In,
ICM is lesser than ICM dash.
in which case mass seems to be more closer. Take some point and think of this. So imagine I take a point on a body. I take a point somewhere here. Try to understand this concept. Now, how far this point is from the pink line and from the white line? Or choose any point here. Let's say I'm choosing a point. This is the mass of the disk. Now, this point is at a distance of r from the white also and from the pink also. Correct. But if I choose a point somewhere here, it is quite close to the white, but more away from the pink. You can see that. And if I choose something on the line of white, then it is zeros from the white, but again some from the pink. So by common inspection, we can say that the mass is relatively closer to the white axis than the pink axis, isn't it? Do you realize this?
Yes, so
So now tell me which one is the smaller, the ICM dash or the ICM?
ICM dash is small.
Definitely. Now that should be the intuition. And what I'm saying is that before you study any formula, can you develop this intuition about centrum moment of inertia? Because that is what matter in the universe. So rotational dynamics is easy if you understand this moment of inertia part. So when we have multiple ICM, then the one which lies in the plane of the body will be least. That's for sure. So if you have a planar body and then if I draw my infinite center mass axis, the one in the plane will be definitely least value. Because when you draw a line which is normal to the plane, that cannot be the least. And you can feel that because if I draw something on a plane of the body, then many mass will come closer to that axis. Do you realize this? Yes or no? No.
Yes.
So moment of inertia is the measurement of relative distribution of mass around the axis of rotation. And it gives you the idea that if it is closer to the axis, then okay, let's take this simple example. This will help you in realizing something. And this is also like a theorem actually. So let's say we have two particles, M1 and okay, and let's join these two particles M1 and 2 by some length. So I can draw infinite axis. So let me draw this axis somewhere randomly here, which is at a distance x from the one mass. And so now moment of inertia is a scalar. And if I is a scalar, which means what does it mean? The moment of inertia of each particle you can just add mathematically, like into the algebraic addition. Therefore, for n particle system, just add I for each particle algebraically. No need to worry about mathematics. Just you think of the distance and just take the value and add it. That's it. Now this diagram is equivalent of this diagram. So if I remove this mass and if I just draw the mass something like this, it is same thing. Even if I put this mass here, it's the same thing because what matters is the distance, not the location. So whether it is on the same side of axis or on the other side of axis, that doesn't matter. As long as it is distance x away from the axis, all are said to be unique or you can say similar configuration. So configuration of mass around the axis is defined by the values of the distance from the axis, not on the orientation, and distance here refers to the perpendicular separation, not any line. Okay. So question is find I. What is I? Tell me.
M1x plus M2 L1.
M1.
M1x square, sorry, plus M2 L minus x square.
So now minimize I. Choose X which can minimize I. Find I minimum because it is a function of X you can find.
So we have to differentiate.
Yes. So to minimize this I have to differentiate. And can you differentiate everyone? And put 2 0. If you differentiate and put 2 0, you get the X value. Tell me the X value how much you get. Tell me the answer, guys, please.
So 2M2L upon 2M1 plus 2M2. Sir, M2L upon M1 plus M2.
Correct. So X equals to M2L upon M1 plus M2. Correct.
So this
Now
is
what
center of mass location. No?
exactly? Now that is the crux here. That if you have any system of particles, then the axis which will pass through the center of mass will offer you the least rotational inertia. So the nature has a choice. Okay, so nature will prefer. So nature decides that okay, if you give some, if you just throw, let's say you take a like any, just take a book or anything, right? You just take it. You take a coin. That's the best one. So when you toss a coin, then have you seen the spin of the coin? Have you seen this? Everyone,
Sir, what?
if you take toss of coin, have you seen the spin of the coin? Have
Yes.
you ever observed? Okay. So no matter how you hit the coin, it will spin around one particular axis, which happens to be the axis passing through center mass. And not only that, that axis will be the diametric axis, the ICM dash. Why? because that is the least value. And nature always start the spinning about the axis which is the least difficult. In a way, that is a natural choice for the nature. Nature will always pick the least difficult task by default. So it means to understand which axis is the axis of most preferred rotation, no need to calculate anything. Just throw in air and check the motion. You come to know, okay, okay, this is a nice, okay, this is something interesting. So now nature will already, it will have the natural choice to pick the one which is the least difficult, because see, the least difficult will get activated the first. That's simple idea, isn't it? So the
Yes.
difficulty is, the nature follows this difficulty rule, and by default it is the center mass. So now if we pick center mass as a preferred choice of rotation, then among all parallel axes which you can draw to this axis, so among the set of parallel axes, among all this set you can draw axis anywhere, the ISM will be least. I'm saying among the parallel set of axes, not the other axis which is not parallel, because among that we can have a different criterion to decide the least value. Okay. So this is like a theorem. You can say that for a given set of parallel axes, the axis which will pass through center mass will offer the least moment of inertia. Now let me put this theorem and note that. So among a given set of parallel axis.
So this is only for two particle system.
No, 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 for anybody. Two particle system I have taken to demonstrate. Okay, because for other I cannot demonstrate, right? So among a given set of parallel axes, the axis which passes through the center mass will offer least moment of inertia. Okay. So we'll do one or two discrete problem, then we'll go to the body problem, like how
I
to.
If
want to
I'm
know
not
the
sure.
last.
No.
Okay. So let's do some basic problem, then we'll go to the challenging one. So sorry. So this is some sort of equilateral triangle. This is the center of gravity, or you can say centroid. So I have drawn three axes, as you can see. I1 you can see I2, the x-axis, I1 is the y-axis, and the third is the right into the plane, like it's a normal to the plane actually, so you cannot see the axis. Okay, so this is called the perpendicular axis, and this is basically the centroid or center mass. So you have to find I1, I2, I3. Solve this. So this is easy problem. Then I will give some one or two difficult problem. Then we will go to the continuous body.
Sir, at ICM there is the principal axis. Sir, at
Pardon?
ICM the axis of rotation is there at ICM.
Yes, yes, that is the axis of rotation.
Sir, I2 is ma square by 4.
How much? I1 is how much?
Sir, I2. I2 is ma square by 4.
M
A square by 4.
I2 is root 3 a by 2. What is the right? So,
Sir, what we take horizontal distance? Perpendicular distance.
see, this is 0, na? The one which lies on the axis will be 0 distance, right?
Yes.
Now only one mass is there, na? At a distance of root 3 a by 2. Correct? When you take I2, then how far is this mass from I2? 0, 0, 0. So the one which lies on the axis of the rotation, they will have 0 moment in it, 0 contribution to the rotation. It means it is very easy to turn.
Sir, so I2 will be also 0, no? As it is on the.
Pardon?
So I2 and sorry, I2 and I3
We
will
have
have only.
three mass. We have three mass. 1, 2, 3. So you have to find for all and add. So 2 and 3 is 0. But the one is not on the axis. No, one is away from the axis. How far? This is the distance. No? You need to realize this part because see, most of the students they fail to understand the perpendicular distance also. That's the problem actually. You need to see this distance clearly. If you're not getting the distance, then you need to rethink about what I said.
Sir, I didn't understood the diagram, sir. Please will explain.
First, you need to realize what is the axis. So this is the line. Now look at each mass separately at one time, one mass at one time. Now look at this mass. How far is this from the axis?
Sir, which is the rotation, axis of rotation?
When I say I2 axis, then I am turning like this. No? you,
Sir,
you,
it
should
will
just
be 0.
you just need to find the distance from the axis. I mean, that is obvious. And not about this, this is also 0.
Yes.
How far is this from this
Root
axis?
3a by 2.
Yes, that's the answer. So where is the ambiguity? Where is the problem? The problem is you're not trying to realize what I'm saying. Like you're not trying to understand the distance concept. That's it. So what about I1? Tell me, guys.
It will be m into root 3a by 2 whole square. Only a root 3a by 2 square.
So senseless now. You guys have no sense of distance. That's a very, very bad thing. See, if I draw some axis, then the distance will be this distance. Come on. I mean, what do you think of distance? I don't know. What is running in your brain? You need to rectify that process. So rebuild the process of distance. You have the axis and you have to think of distance. Come on, guys. Try to realize this. I mean, at one time, one axis. And then check each mass separately. For I1, if you look at this mass, what is the multiplication?
Sir, 2 into 2m root 3 by 2 whole square.
You guys are of no use. I mean, you don't understand the distance as what I can do. I cannot teach you the distance. This mass is half from this axis, a by 2. This is how much? A by 2. What is the problem? You don't know the meaning of distance, no? What I can do? I cannot teach you.
Sir, I
You guys.
cannot see the rotation, axis of rotation.
It's called I1 means what? This axis.
Okay.
I2 means this axis. And this is the axis which is normal to the plane which you cannot see. Now, what else I can teach you? Tell me? If you have some doubt, you can clarify
Okay,
the
sir,
doubt.
understand.
Once your doubt is clear, then you can do this question. So you all got the meaning of I1 and I2?
Yeah,
Yes.
sir, understood.
Sure. Do this. The I1 is pretty easy. The first will have 0. The second will have m into a by 2, as you can see, whole square. The
Yes.
third will have
Sir,
a. It's the same value. So basically, it's m a square by 2, I think, right? So what about the I3? The distance is this one. Can you see that? Okay. It's 3 dimensional. You can put a pen normal to the plane, and then you can check the distance, how far it is. You put a pen like this, normal to this point. Yeah, somewhere. Okay. You put something here. Take a pen, put it here, and then check the distance. Imagination. Huh?
Sir, I got MA
Sir,
square.
3m a by root 3
How much? 3m?
a by root 3 whole square.
Correct. So that the answer is ma square, right? So it's 3 times of, that's the same distance. M into the distance is a by root 3. If you apply
Yes.
it to,
So it will be MA square only. Yeah,
correct.
I got MA.
And you can see among all this, which is the least?
Sir, MA square by 2. I1.
Because I1 is in the plane of the body, and ICM is, of course, see, I1 is also passing through center mass. You can see I1 is also ICM because it is also passing through center mass, and I3 is also center mass, but one is in the plane will have lesser value than the one which is perpendicular. And if, okay, now this is the easy one. So how many of you are not able to get the answer? Just message me. Let's say I'm not able to get any answer. Srishti, Swam, Harshit has nothing. Atharv, Saman, Atharv, this
Sir, I
Pandya.
told the answer.
Yeah, sir, I
Yes.
also told the answer MA square.
Yes.
Who else are not getting the answer? Okay. Good. Message me. Those who have not got the answer, message.
Sir, then it will rotate in the I1.
Hmm?
Sir, then this will rotate in the I1.
Yeah, if you just throw it randomly, if you just give a, I mean, twist and throw, it will take the least one. So I1 is the least one. I mean, naturally, if it will set into rotation, it will take I1. Okay, so now let's do the next one. So you can see this is a, a cube of side A each, and all masses are identical. So now there are three axes which I can draw. One I will take as a one is called the edge, the axis which is containing some edge. One axis I can draw which is containing some face. Maybe I should. And the other definitely will be the the body diagram, right? There are three types of sides which we generally talk in case of cube. This is the body diagram, BD. This is the face diagonal, FD, and this is the edge.
Sir, that I edge one, I got 4ma square plus 2ma.
I edge is how much?
4ma square plus 2ma.
2ma square. All will have square only. No? How much is net answer? How much ma square?
Eight m square.
And what about the I face? Okay, so the answer let me give you. This is 6 and this is 4, and you can prove in a tutorial. Okay, so I'll not spend
So
time
that would be 18 square. Sure.
here. 864 are the answers. You can just go, I mean, in tutorial class. You can just discuss with answer. If in case you don't get the answer, or you can practice at home. So this is the last one. Now I'll go to the continuous mass distribution. So if I do any body,
So is that mi?
pardon,
So is that mi?
yeah, it's m moment of inertia. So I choose some random axis here, and I want to find the moment of inertia. Of course, we know that we cannot do it for a body. We only know for a particle. So what we can do is we can cut one particle here. Now we have a particle here. We must make a lot of cut. And then I just need to know the distance of this particle from the axis, correct? So how far is this? And let's say the mass is, let's call dm. So the moment of inertia di, the elementary contribution, will be dm into r square, because that's the formula which we know already, that we are sure of. So for finding the net value, I have to integrate. That's it. And the derivational part is same, the way we have learned the derivation of finding the elementary or taking the elementary. The only difference is the formula. So earlier, if you remember that earlier you were trying to find YCM, XCM or whatever. So you used to at YD, and then you used to substitute DM as per the cut made and all, and then DM. Now here it's a pretty simple. Here things are like DM is also there. So you have to make some cut like this. But the formula is R is per DM, which is pretty easy. The distance. So let's apply this quickly. So let's take a rod. So if I take a thin rod, and if the axis is passing through the center mass of the rod, it's ICM actually, which is attached to the rod length. Okay. So this is mass in. Sorry. This is L by 2 both sides because center mass. So what is the moment of inertia? So now it really doesn't matter whether it is on the one side or the other side, because if I know the answer of this part, I can just double the answer, right? Or you can integrate both sides. And that's, you can just start cut one elementary here somewhere here. X square dm, and you just integrate. So you know the elementary, how to take elementary in case of linear objects. So that's very easy. X square dm gratis. So when you go x, you contain length dx. So this length is dx, we know, and we can write the answer in terms of dx. The dm we can express as dx, which you know in fact. So m by l dx, lambda dx. Right? And once you solve, what is the answer? Tell me. What is the answer?
M by M by 3L.
Solve will give you the last answer.
M square by L.
Sir, I am getting 0.
Pardon. Okay,
Sir, ml is square by 12.
that's correct. Well, it cannot be zero, no? It's x cube by 3 will add up.
Sir, it's not 0.
So now do the same question with putting the axis at one end. What happens if I put it here? So what will it increase or decrease? Tell me, guys.
Increase.
It will definitely increase because now center mass is quite aware. In fact, the mass is from 0 to up to L separation. Earlier it was only up to L by 2. The maximum farthest mass was L by 2. Now the farthest mass has gone up to L. So it's quite increase. So now you will have okay.
Sir, ml
You'll
square
have
by 12.
how much? MS double?
12. Acha, sir, okay, that I'm asking for that.
So calculate the same question, but for the end axis, not the axis in the center.
0 to 1.
Yeah.
ml square by 2.
Correct. MS double 3.
This is bigger than the last year.
See, once you know the elementary, it's only a matter of formula, like how you substitute the answer in the formula, and you're done. Okay. So let's do some Rotational problem. If I give you a ring, that's pretty easy. And now the axis is actually normal to the plane, which is a blessing in disguise. So now the answer is only for this particular axis. You cannot just say that this is for all axes. Right? Now this is the axis which is right angle to the plane, and let's call it this is IC. And the ring will have the axis ring will radius, let's call it radius R. Now no matter where you look on either side, every particle on this ring will have same distance. How much? R. Isn't it?
Yes, sir.
So distance wise there is no variation. That is something interesting. Distance wise there is no variation. And therefore it is as good as a question of particles. So whether you put a particle at one point here or you spread over the ring, it is similar configuration. Configuration is same because the mass is having similar distribution. It is not closer or farther. Therefore, you can directly get the answer as m square. I hope this is clear. Because every dm, if you choose any dm, the answer is dmr. Other dm, dmr. So if you just integrate what you get, this is outside. Because r is same, r is not variable. So for ring, pairing, you can directly get the answer as m r square. Correct. Now, what is more interesting is what happens if I make the ring into half. So what if I have a half? Now tell me, what if I make the ring into half? It's the same axis, same ring, but instead of full, it is half. What do you think? The answer will change or remain same? Tell me, guys. What do you think? The answer will be same or will change?
Same.
Exactly. It's the same. Why same? Because the distance I haven't changed, because all mass is
Yes.
still at r distance. So what really matter is the separation of individual mass from the axis, not the shape of the object, shape of the distribution. Therefore, as a intuition, if you try to develop the intuition, look at the each point separate, and then try to look at the distance also. And once you realize that the distance is same, the answer is going to be same. Okay. So now, even if I draw a simply an arc, if you draw an arc, now what do you think? If the r is radius, if the m is mass, what is I going to be?
Mass flow.
So no matter what is the shape, because see the distance I'm not changing. So all are a similar configuration. Even if I, again, if I just put everything at a single point mass, it's the same. So a ring is equivalent of a point mass. Understood? But not only this, imagine this image. I mean, just try to create this intuition. So this is the axis. And if I give you a rod, so what is the moment of inertia of this rod? This is the axis. So what is the answer, guys? Tell me.
So MR square.
MR square.
Correct. So it's again MR square. So like the same logic. And now imagine that if I eventually create a if I eventually create a so if we eventually get a hollow cylinder and if I draw the axis, it is easy for you to realize it. So what is the moment of inertia of this entire cylinder?
MR square.
See, it's all are same answer because see, all refers to the same configuration. So it's just like I have just distributed the mass in a random shape and then I have preserved the distance pattern. So distance is scalar. So MR square is a formula not for one object. So it's a formula for anything which is at a distance r from the axis of rotation. Means no matter which point you choose on the body, if all happens to be at the same distance, the answer is MR square. So now when we do the integration, only when we have to see that okay, the different masses at different distance, then we cut the elementary and use the formula and then integrate. So now you realize something, I mean, more intuitively, like this is the way to go ahead. And then if I give you a disk, okay, so earlier I was giving a disk. If you remember. So now it's a disk of uniform thickness. So don't take otherwise. It's uniform thickness. And if I have the axis, the mass is in and the radius is let's call it vector. So of course there is no formula for the disk. So you know the formula for ring because you have just learned about it. So what you can do is you can cut into small rings and use the formula which you know and then integrate. So it can tell me the answer. Are you guys solving this? Yes or no?
Yes, sir. Sorry.
Solving
Okay. Go ahead.
Sir, the thickness is what?
You are not supposed to consider thickness. It's negligible.
Yes, sir.
Okay, what is the answer, guys? So you know what is the step to do, no? This is simply you just need to cut an elementary ring at some random radius. And why this so? Because because you know the answer. So if you know some answer, then you should do this. That's the only idea. So you move R and cut a dr thickness. So you got the dm. So now you can add the di answer. Di is how much? Dm r square. That's it. Now what is dm? So because it's the surface, so you have to use the surface mass density, and you know how to add this. You can add sigma into dA. Now the process is same, only the difference is formula. And then sigma is how much? Okay, we can put it different. dA we can write as 2 pi r dA. We all know this already. And we are done. Okay. So sigma is a constant quantity, so we can substitute at the end. If it is a variable, then they will mention it. So we can write 2 pi. Okay. So what is sigma actually? Mass upon area. So we'll get the answer as m square by 2. Correct. And this is obvious no? Because the same mass is now distributed from 0 to r instead of only at r. So mass is closer to the axis till up to r. No, the same mass m now I'm keeping from axis till r, so it will be having lesser uh, variation. So it is now closer to the axis relatively to the ring case, and so the answer is reduced. So every time we are using the same mass and same radius, so that we can compare the things. Which one is bigger, which one is smaller. Now, when you get the answer for disk, a cylinder is a continuation of same thing, right? So if I make a cylinder which is solid cylinder, then you can imagine mentally that this is a collection of disks, and because each will contribute the answer dm r square by 2, so the net will be equals to m r square. It means there is no apparent difference between the a thin disk or thick disk, which we call cylinder. So whether it is thin or thick, both will have same answer. So this formula is equally true for the for what? Hello guys.
What's
Hmm? For cylinder. So for solid cylinder, the I is again keeping the axis same. So of course I am not changing the axis part. So if you have a solid cylinder, then answer is same. So it really doesn't matter if it is thin, because see by shrinking it, you end up getting the same thing repetition. So when you shrink it, the mass distribution is not changing in terms of separation from the axis. So whether it's a thin disk or full cylinder, if the mass is m, vertices are, the distribution is equivalent. So the answer is same.
yes.
So now imagine if I give you a rectangular sheet. Okay. So if I give you a rectangular sheet of length L, width B, and if I give you axis, again the same. No need to solve this question. I mean, you can just tell me the answer. What
Mars.
axis? If it is passing through the center of mass, and if I call it I1, and if I call this is I2, what is the I1 answer? Without solving, what is the answer? What this should be? M is a mass.
M square by 12.
Correct. So it is same as the rod problem, because eventually the mass which we have is spread down will not affect the answer. It is still by 12. What about I2 then?
NB square by 2.
Exactly. So it really doesn't matter the
I didn't
shape.
understood that.
Pardon?
No, sir, not understood.
So you can do thing, no? You can take a plain paper and you just fold it like a rod. You know how to fold a paper. So when you fold a paper from, let's say, if I start folding from bottom, if I folding start from here. So after folding, it become a rod like this eventually, right? Just wrap from the bottom to the top. So if you start folding from here, this edge, and if you make a roll, a thin roll, in the process of rolling, tell me the mass distribution is changing, yes or no? Is the mass going away from the axis, coming close to the axis? Tell me what is happening for I1. For this axis, if I fold from bottom, if I just wrap this to make a
Coming
roll,
closer.
eh? Are you sure? Let's say if I fold into half, if I'm not able to roll, you can fold. So fold about this axis, so it will come half like this. Now if I fold this paper, what do you think? The ion will change, yes or no?
No, sir.
No.
If I fold further, then
No change.
if I keep on folding till infinity, it will become a line, correct? So
Yes.
will it change? Now that is the question. By folding or by wrapping or rolling up from bottom to the top, is ion going to change? The answer is no. So it is same as the question of a rod. Now. The other way of thinking is you cut an elementary. So just take a piece of it, and this piece will give you the answer how much? dm L is over 12, correct? So the entire sheet is a collection of such pieces, no? 1, 2, 3, 4, 5, 6, 7, infinite. So if I add all value, what I'll get? M is over 12 into integration, and this is constant, so you can take. So now the the whole idea is that once you know one formula, can you actually think in more sophisticated case without actually doing the integration? Because this is the intuition part which I want you guys to develop. No need to always solve the question from scratch. So that is not required. So cut elementary mentally. You just do it mentally, and you can see, okay, this answer I know, and this is a continuation of the same answer. So I know the answer directly. So now for the sheet, you know the answer for each axis. Now, if I draw one axis which is something like this, it is challenging for you. Now you don't know the answer because here we don't have some elementary which I know the answer. Or I can cut and I can solve. So that's going to be challenge. So that we'll see how to do that. Okay. So now because you know the basic formula, I mean I'm expecting something more from you. So solve this question. So now we have a triangular lamina, the sheet in shape of a triangle. and you can draw two axes, one from this side.
So join
not
to
a-
the A side.
Yeah, so this is the right angle. So this is the axis I'm asking the question. So if I call I1, I call I2. So mass is so find the answer of I1. Yes. If you know the one answer, the answer is obviously the A will be replaced by B or B by A. So find the moment of inertia about any one axis. You just find I1 or I2. And you know the answer of a rod, so you can how to convert the. If I give you a triangle, then what you can do? You can convert it into thin strips, which are like a rod, and you know the answer of a rod. And because you know the answer of the rod, you can integrate that answer. So choose variable. So anyone trying this question?
Yes, sir.
What? So I think you have taken too much time. So again, it's the simple. You take elementary like a rod. And for the simplicity, I have taken this as x, and I have taken this as y. And this mass I can set d. So di2 will be how much? So now if you know the answer for rod from the end actually, so dm L square by 3, m A square by 3 if you remember the formula. So because we know this answer from the very beginning. Yeah. So you can use this formula actually. And the next step is simply integrate. But dm connect is sigma dm, which is this is y dy, because if you move y and cut dy, the area will be how much? Now dy is the variable like integrator which is y, but x is the variable. I need to substitute either x as y or y dy as dx. From the triangle property, we can add as x by y is same as b by a. That's tan theta. Sigma triangle. So x is b by a. You can write as, there are two choices. Either you substitute x from here in terms of y, and then you indicate y, or you can do other one. It's up to you. So now I can write as, so what I'll do is I can change the variable integrator one. So I can write dy as a by b dx. Now this is easier. And next we go from 0 to b. So mass is sigma into area. The answer is how much? So what you're getting is mb square by
MB
6.
square by 6.
So now the other is simple. I need not to solve this. So I can directly say that I1 will be ma square by 6. What matter is the farthest point from the axis. So for I2, B is the farthest point, and for I1, A is the farthest point. That's matter. So now this formula is going to be very useful in all other calculations which are challenging one. So practice this once again. And other derivation which are peculiar derivation, like we'll do it. So you can do, let's say you know the disk answer, so or ring answer, you can do it for the hollow sphere, solid sphere. You can do those calculations. You can do cone calculation about the axis, because eventually it's a ring or disk only, right? So you can take this as a homework and only come back with answer. So your homework is cone about the axis of symmetricity, because in cone we can have many axes, but I want you to do with symmetrical axis. So you can do this axis, and you can take the radius as r, and height will not matter. So in all calculation, what will matter is r, because the axis is this, and the distance will go from 0 to r. So the r will matter. The height will not matter. You can choose whatever value you want. So do it for the hollow cone, hollow solid cone, and then hollow sphere and solid sphere. About this axis, about the axis of symmetry. So solve for, and the rules are simple. You have to use the previous derivations as a ready-made answer. So for hollow cone, the answer is simple. It's for hollow cone. For solid cone, it's for a hollow sphere, it's 2 by. So you can just solve and get the answer. So don't get the answer, then you can do it in.
Please below, so page number 13.
This
Yeah,
one?
done, sir. Done, sir.
Okay, fine. So now this is the place we'll stop for today's lecture. I'm not at all okay. So this derivation you do
Sir,
it,
what
and
is FC?
solid, I mean solid cone, hollow cone, solid cone, hollow sphere, solid sphere. So do this derivation. These are pretty much available in any book, and then we'll do something advanced. This is something very basic. In case if you don't get, you can ask in tutor. I will also apprise Amritsar to get this done in the class, and the rest we'll do in the lecture. Okay? We'll do something more advanced. Practice, guys. Those who are preparing for medical, I mean, just remember the formula. For these derivations are not required. So I will tell you what kind of derivations are required. So for medical, only rod problems are asked as a derivation. So you need to know the rod answer. Like you need to know basic derivation of a rod and yes.